In this video, I want to talk about the idea of generating functions, and they're a nice compact way to study sequences. And the sequences we'll be studying will usually involve counting things parameterized by the natural numbers, or something like the natural numbers. So this is an excellent tool to help us do this. So the whole idea here is we want to use those properties of series that we've learned in Calculus 2 and some algebraic manipulation to study these sequences a little more easily. This is a very powerful tool that allows us to do this. So the generating function of a sequence, and we'll say the sequence A1, A2, all the way to A infinity, if you will. And usually we can, I shouldn't say usually, but we may denote this rather than writing it kind of as a list with commas. You might see something like this, AN, where n goes from 0 to infinity. So you might see that to mean this sequence here. And basically, you're thinking of these guys, each element of the sequence, as the coefficient of the x to the nth term. So the nth term in your sequence is the coefficient of x to the n. And I'm missing an A0 here, so let me put this in. That's A0. And again, the only reason I wrote it A0 here is just because it matches the notation here. But with some reindexing, the bit where you start off doesn't really matter. But for our purposes, for this definition, we'll say that A0 is the first term of our sequence. And just like before in the last video, we're thinking of x as just some sort of formal variable. It doesn't stand for a number or anything. It's just a placeholder to keep track of what these coefficients stand for. So if I have a coefficient, say, if A3 is 5, for example, that'll be 5x cubed will be this term. So that tells me that whatever we're counting where n equals 3 is the coefficient of the x cubed term. So this is kind of like a placeholder. But it does have nice algebraic properties, and that's why we're doing this idea. So let's look at a few examples. And these are kind of very simple examples, but they should give you an idea of how this encoding works. So let's say that whatever we're counting, no matter what n is, there's only one of them. So all ANs are 1. So we want to encode the sequence 1, 1, 1, 1, 1, just infinitely many ones, into a generating function. So what would this look like? Well, this would look like our A of n in this case, or A of x, sorry, would be n equals 0 to infinity. And our AN is 1 for everything, so it's just 1 times x to the n. And this is just our simplest power series, so we know that we have a nice algebraic expression for this is 1 over 1 minus x. And let's say that we had a different sequence, and now our AN is n. So whatever we're counting, there's n of them for each n. So how would we encode that? Well, let's write down our generating function here. Maybe I'll do it in a different color. So here, A of x is going to be our formula for our term in our sequence. So AN is n, so it's going to be n times x to the n, as n goes from 0 to infinity. Now, we're not quite at a stage where we know this, but if you remember from the previous video, we do know that 1 over 1 minus x all squared is the same thing as the sum of n plus 1 times x to the n. And sometimes I'll be very loose with my indices. If I don't write down some indices, think of them just being n equals 0 to infinity here. So can we do some algebraic manipulation in order to make this look like this? So maybe first, we can notice that this is the same thing as indeed if we took our series that we know, n plus 1 x to the n's, and we subtracted off 1 x to the n from each of these guys. And remember, addition is commutative, so everything behaves nicely. We can kind of regroup it for each term. Nothing crazy happens there. And we can do that. So here we have. So now, well, we know these two power series, so we should be able to put them together to come up with a nice expression. So I know this guy here is 1 over 1 minus x all squared. That's this guy. And this guy, so we're subtracting off 1 over 1 minus x. That's the function with power series representation, this guy. And we can do a little bit of algebra to simplify this. Maybe we'll get a common denominator, so let's multiply top and bottom of the second guy by 1 minus x, so I'll just make this a 1 minus x here. And then we can see that this simplifies, so we have 1 minus 1 is 0 on top, and we're left with a minus x, so this becomes a positive x, so x over 1 minus x all squared. And now we know that all of the information about our sequence is encoded just in this function. Remember, to get at this, we just need to kind of go backwards. We need to look at the coefficients of this. And remember, to get at those, there's lots of different ways, but one way that pretty much works all the time is we can always take the derivatives at 0 and divide by n factorial like a Taylor series. So this expression here encapsulates the count here, where an equals n. And that's kind of the most important idea, is this encapsulation of the sequence here in this function. And that's really neat. And finally, we have an is 1 for even n and 0 for odd n. So our sequence looks like 1, 0, 1, 0, etc. So when we have an even index, we have a count of 1, and we have an odd index, we have a count of 0. So if we think about this, let's write out the first few terms. So our a of x in this case we're going to have 1 x to the 0, since a0 is 1, since 0 is even. And then we're going to have 0 x to the 1s. And then we're going to have 1 x squared, since 2 is even, so we're going to have 1 of that term. We're going to have 0 x cubed, since 3 is odd. We're going to have 1 x to the 4th, etc. And if we think about this, we can view this as 1 plus x squared as our variable, plus x squared squared, plus, I'll do one more, x to the 6th is x squared all cubed, etc. And, well, we can use our idea of power series again. We know the power series of 1 over 1 minus variable is this guy here, so 1 plus variable squared plus variable cubed. But now our variable is x squared. So we can say this is 1 over 1 minus x squared. So we have this idea of things only occurring on even powers given by this function. Okay, let's see a use of a generating function here. And we're going to use it to determine a closed form, so a non-recursive formula for an if we're given a recursive definition for it. And the recursive definition is the first term is 1, so a0 is 1, and the nth term is 5 times the previous term plus 4. So let's write this down in terms of a generating function first, and let's see if that helps us. So we have a of x here is going to be, and we'll write down the count here. So this is a n x to the n as n goes from 0 to infinity. Notice that the first term doesn't satisfy the recursion relation. It's an initial condition. So I'm going to split that off. So I'm going to take out the first term. 1 times x to the 0 is just 1. And then we have the sum from n equals 1 to infinity now of a n x to the n. All right, good so far. So now what I can do is I can use my recursion relation to replace this an with something smaller. So let me go ahead and do that, or I should say smaller in index. So this is going to be the same as 1 plus the sum as n goes from 1 to infinity. And now rather than an, I'm going to express this as 5 an minus 1 plus 4 times x to the n. And now we can split this up a little bit, and we'll worry about the pieces separately. So I'm going to split this up into 2 separate sums, so 5 an minus 1 x to the n and 4 x to the n. So let's go ahead and do that. The sum as n goes from 1 to infinity of 5 an minus 1 x to the n. And then we have our sum as n goes from 1 to infinity of 4x to the n. And in fact, this expression here looks very close to our power series. We just have the wrong index here. So let's reindex and fix that, and then we'll be on our way. So I'm going to do this one just up here. So let's reindex this. So rather than n equals 1, I'm going to start at 0. And if we do that, what do we have? So let's say m is our new index here. So we'll have the sum as m goes from 0 to infinity, and m is just going to be n minus 1, which means, of course, n is m plus 1. So we have 4x to the m plus 1 now. And we're off by an index, but that's okay. We can view this, if you like, as 4x times x to the m. Take that extra m that we don't want and put it out there as part of our fixed coefficient. So that's great. And now I know what this is going to be. This is going to be 4x over 1 minus x. So that piece is done. Excellent. So let's go ahead and deal with this piece here separately on the next slide, and then we'll put it all together. And we're going to play that same trick by reindexing here. So we'll make mn minus 1, so we'll start at 0. So here we'll say that m is n minus 1, which means n is m plus 1. So that's going to be the sum as m goes from 0 to infinity of, so we have 5a to the m x to the m plus 1. And again, this is looking a lot like what we started with. Remember, our index is now m instead of n, but that's just a dummy variable. It doesn't matter. I have this 5 that's extra, and I have an extra x, but they have nothing to do with the index m, so I can take them to the outside. So I have that this is, so we'll take out the 5x, and we're left with the sum as m goes from 0 to infinity of a to the m, am x to the m. And I'm just going to rewrite this with the variable n in, just so it looks very similar. So this is 5x, the sum, an x to the n. And that's exactly what we started with. So I'm going to call that 5x big A of x. So this is great. We've simplified our generating function. So let's put all the pieces together. So if you remember, we had A of x was 1 plus this guy, which we've simplified to 5x A of x, plus, on the previous screen, you remember it was 4x to the n, which we simplified to 4x over 1 minus x. And remember, we're looking for an algebraic expression for A of x. So let's solve for A of x here. So we'll bring over that 5x a to the x to the other side, so and factor it out. So we get 1 minus 5x a of x equals 1 plus 4x over 1 minus x. And if we just want to solve for A of x, we get A of x is, I'll write it like this, 1 over 1 minus 5x plus 4x over 1 minus x times 1 minus 5x, just dividing everything by 1 minus 5x. So we have a nice expression for our generating function here. That's great. So that encodes our coefficients. Remember, our recursive formula gave us our coefficients, so this encodes that. But remember, we're looking for a non-recursive formula for these guys. So we still have a little bit of work to do. But I'll tell you, our plan is working backwards. So I know that this indeed is a power series. And this I want to split up into two separate power series using the idea of partial fractions here. And if I do that, then I'll be able to combine all of these power series together since I know what they look like as a sum, and that will give me my AN. So let's do that on the next slide. So this is already a power series, this term here. So we just have to turn this, which looks like the product of two power series, into two separate power series using partial fractions. So let's say that we're doing that. Let's use partial fractions here. So we want that 4x over 1 minus x times 1 minus 5x equals something. Usually we'd use a and b, but since I'm already using a as the symbol for the generating function. Let's use b and c. So this will be b over 1 minus x plus c over 1 minus 5x. And we can use the usual technique of multiplying everything through by the denominator. And we get indeed 4x equals 1 minus 5x times b plus 1 minus x times c. And here, there's of course two ways of going. We could always expand this out and equate coefficients for powers of x. That would definitely work. Or we can be smart and plug in values of x that would make stuff disappear. And that's what I'm going to do. So I notice if x is indeed 1, then this expression here is 0. So let's do that. So when x is 1, we get that 4 times 1 is 4 equals 1 minus 5 times 1 is negative 4. So we get negative 4b plus, and of course 1 minus 1 is 0. So that term is just 0. And solving for b, we get that negative 1 is b. And to solve for c, we can do something similar. So to make this term 0, here x needs to be a fifth. So we'll set x equal to a fifth here. So we get 4 times x. That's 4 times a fifth is 4 fifths equals, well, if we plug in a fifth into this term, we get 0 by design, plus 1 minus a fifth times c. So you can see here we get 4 fifths equals 4 fifths c, which tells me that 1 equals c. So we have b and we have c. So after our partial fraction decomposition, we can indeed finish this off quite easily. So we know a of x now is 1 over 1 minus 5x plus, and then rather than putting this combined expression, we'll use its partial fraction decomposition. So this is going to be negative 1 over 1 minus x plus 1 over 1 minus 5x, which we can simplify to 2 over 1 minus 5x minus 1 over 1 minus x. So we're almost there. Let's bring this to the next slide and write this in terms of power series themselves, and then we should be able to read off the non-recursive formula for an. So here's our formula for a generating series that we simplified using partial fractions. So remember, these are indeed power series. So I'll take that 2 to the outside. So we get 2 times 1 over 1 minus 5x minus 1 over 1 minus x. And here I can think of 5x as my variable, and of course x is my variable in the second one. So I can view this as 2 times the sum of 5x to the n, as n goes from 0 to infinity, minus the sum as n goes from 0 to infinity of x to the n. And maybe I'll rewrite the second one, if you like, as 5 to the n, x to the n, minus the sum of x to the n. And now I'm going to combine everything into one sum. Remember, this is just things summed together, so I can group according to powers of n. So I'm going to do that. So this is going to be the sum as n goes from 0 to infinity of 2 times 5 to the n minus 1. So the 2 times 5 to the n comes from there. And the minus 1 comes from that term. And that is times x to the n. So what did I just do? I wrote my generating function, a of x, in terms of something, some coefficient, times x to the n to the appropriate indices. So this here is my coefficient. This is my formula for an. An is 2 times 5 to the n minus 1. So there is a nice technique to be able to find non-recursive formulas for sequences given by recursion relations. And in the next lecture, we'll continue on with this idea. There is so much to do with generating functions. We'll see a bunch of really cool things.